In this video, we want to introduce the idea of a cross product. And we take the cross product of two vectors, and so it looks like this. If we have the vectors A and B, so we have the vector A and the vector B, then we indicate their cross product with this times symbol. So we would read this as the cross product of A and B. And the cross product is the vector that is orthogonal to both A and B. So if we maybe had a picture like this, let's say this is the vector A, and maybe this is the vector B, then the cross product might look something like this, where it's orthogonal to both A and B. So this here is A, this is B, and then this is the cross product. So the cross product A times B, and we'll make those vectors. This is the vector B, and this is the vector A. So in a way, you can see it's orthogonal to both. The cross product vector could also point this direction, and we'll actually talk about later how to determine the direction in which the cross product points, but the idea here is that if you have two vectors A and B, the vector that's orthogonal to both of them is going to fall somewhere along this line, but it could point in either direction. So we'll talk about the direction, we'll talk about determining the direction a little bit later, but right now, let's talk about how to calculate the cross product. So if you have two vectors in three-dimensional space, then the cross product looks like this. We calculate it with what's called a determinant, and it looks like a matrix, but it isn't a matrix. In the first row here, we put the standard basis vectors I, j, and k, and then we put the vector A, its three components, and then the vector B, its three components here in the last row. And you can tell that this is a determinant and not a matrix because we have straight lines here, whereas with a matrix, we have brackets. These are bracketed lines instead of straight lines. So when you see the straight lines, you know it's a determinant, not a matrix. And we have a whole section later on where we're going to talk all about determinants, how to calculate them, what they mean, their properties, what we can do with them, everything. So right now, we're just going to stick narrowly to how to calculate the cross product, and we'll get much more into determinants later. But the idea here for calculating the determinant is that no matter how large the determinant is, we always want to break it down into 2x2 determinants because 2x2 determinants are easy to find. And right now, we have a 3x3 determinant. So what we want to do is we want to start with the first value in the determinant in the 1, 1 position. So that's I here. And then we want to look at everything that's outside of the same row and column as I. So we ignore I's row and we ignore I's column, and we look at everything else that's outside of it, which would be this value here. So when we look at those two, we break this determinant apart this way. We'll say this is equal to, we take I as the coefficient, and then we multiply I by the determinant of this other part that we've boxed here. So A2, A3, B2, B3, and then we move to the next piece. So we ignore this for a second, and we move to the next value in the first row, which is J. And then with J, again, we ignore the row that J is in, and we ignore the column that J is in, and we look at everything else, which would be these values here. And so with J, we put together a 2x2 determinant. So we say J, and then we multiply that by the determinant A1, A3, B1, B3. Notice how we're leaving the orientation of these values the same. And then we go to the last entry in the first row, and that's K. And then we look at everything that's outside of K's row and column, which is this value here. And we put those together. So we say K, and then we multiply that by the determinant of A1, A2, B1, B2. So we've now broken apart this 3x3 determinant into 3 2x2 determinants. The only thing we have left is the sign on each of these determinants. And for the sign, we really want to remember the checkerboard pattern. So we always use this checkerboard pattern when it comes to determinants. we always start with a positive sign in the upper left-hand corner, and then we alternate across every row and down every column. So if we're moving across the row, we would say minus, plus, and then we're moving down the column, we would say minus, plus, plus, minus, minus, plus. So we have alternation everywhere. So for the coefficients on I, j, and k, we would match those up to their signs. So we would say that I matches up with a positive sign, we would say that j matches up with a negative sign, and we would say that k matches up with a positive sign. So in our string of 2 by 2 determinants, we put a positive in front of I, we put a negative in front of j, and we put a positive in front of k. And now that we have 2 by 2 determinants, 2 by 2 determinants are really easy. Because to find the 2 by 2 determinant, we simply cross multiply. So we multiply the upper left by the lower right, we say A2, B3, and then we subtract from that the other product, A3 times B2, the upper right times the lower left, upper right, lower left, and we follow that pattern for every 2 by 2 determinant. So upper left times lower right, A1, B3, always minus, and then A3 times B1, A3, B1. And then we say plus K times upper left, lower right, A1, B2, always minus, and then upper right, lower left, A2, B1. And that's how we simplify a determinant. So let's go through and do this with an example. Let's say that we have the vector A, and that vector is equal to 1, 0, 2, and then we have the vector B, and it's equal to, let's say, -2, 1, 0. If we plug that in to a 3 by 3 determinant, we have I, j, k, then we have 1, 0, 2, and -2, 1, 0. And then that's going to be equal to, we'll take a positive I multiplied by 0, 2, 1, 0, everything outside of I's row and column, 0, 2, 1, 0, minus j multiplied by everything outside of j's row and column. So we have 1, 2, -2, 0, and then plus k multiplied by everything outside of k's row and column. So 1, 0, -2, 1, 1, 0, -2, 1. And then we can do our cross multiplication. So we have I times 0 times 0 minus 2 times 1 minus j times 1 times 0 minus 2 times -2, and then plus k times 1 times 1 minus 0 times -2. And if we simplify, we'll get I times 0 minus 2 is a -2, minus j times 0 plus 4, that's a positive 4, plus k times 1 plus 0, that's a positive 1. So we get -2i, and then minus 4j plus 1k, which of course is just plus k. We could also rewrite that by taking the coefficients as -2, -4, and then positive 1. And this vector, -2, -4, 1, is the cross product of the vectors a and b. So this vector is orthogonal to both a, 1, 0, 2, and b, -2, 1, 0. It's orthogonal to both of those vectors. It is the cross product of those vectors. Now, when it comes to how you determine the direction in which the cross product points, we use what's called the right-hand rule. And it seems silly, but it's actually fairly straightforward. If you hold out your right hand in front of you and you point out your index finger and your middle finger, so you kind of point your index finger out in front of you and point your middle finger sort of back toward your left hand if your left hand's being held out in front of you as well. So you sort of have these fingers spread apart, your index and middle finger, and then you've got your other two fingers tucked in and your thumb pointing up. So if you hold that orientation of your hand and you're able to hold your index finger pointing toward the vector A, and you're holding your middle finger B pointed toward -2, 1, 0, then wherever your thumb is pointing, and your thumb's usually pointing kind of straight up or straight down, wherever your thumb is pointing, that's the direction in which the cross product vector would point. So if you can sort of visualize these in 3 dimensions, let's say we had 3-dimensional coordinate space that looked maybe something like this. So we'll draw our axes here, and let's say we have the x-axis, the y-axis, and the z-axis. So 1, 0, 2, let's say that comes out 1 unit toward the x-axis, 0 units toward y, and then up 2 units toward z. That might look something like this. So that is A. And then B would be -2, 1, 0. So let's say for x, that's -2 would come out here, 1 toward the y would come out here, and then 0 for z. So yeah, maybe right about there. And obviously this is hard to sketch in 3 dimensions, but we're getting the general idea of where these are pointing. So if these are our 2 vectors, A and B, and you try to use the right hand rule, so if you hold out your right hand, what you can see, start by holding it in the normal right hand rule position where your thumb is sticking straight up, and your index finger and middle finger are sticking out like this toward the vector A, toward the vector B, so normal position. If you start there, but then you realize we're trying to match this sketch here of our vectors, A and B, what you realize is that you have to take your hand and turn it in toward your body, turn your thumb down and toward your body, so that your index finger is basically sticking straight up and a little bit to the left to match our blue vector A, 1, 0, 2, and then your middle finger is sticking out away from you, kind of pointing toward your right-hand side to match our yellow vector B, the -2, 1, 0, which you can see sort of leaves your thumb pointing toward the left, a little bit down and toward the left if you've done this with your hand. So we should be able to get a sketch of the cross product vector that seems like it matches that. And in fact, if we sketch this cross product vector, -2, -4, 1, we'll start here again at the origin, and we'll move -2 toward the x direction, maybe something like that. Then -4 toward the y direction. So that's going to be maybe all the way over here, and then up a little bit, just 1, something like that, along the z-axis. And so the vector looks something like that. And roughly, with our right-hand rule, that's what we would have expected. We would have expected the cross product vector to point off here toward the left, because when we rotated our hand around to try to get our index and middle fingers to point toward A and B, we had that cross product vector pointing somewhat toward the left. The last thing we want to do is make the point that we can find the length of the cross product vector. And so as you know, we write the cross product of the vector A and the vector B this way. So if we want to express the length of the cross product, we make it look like this. That's now the length of the cross product vector. And we can either find that using this formula, where we say the length of the vector A multiplied by the length of the vector B multiplied by sine of theta, where theta is the angle between the vectors A and B. Or instead of using this formula, we can simply use the distance formula to find the length of the cross product. And that formula, of course, will just be that the length of the cross product is going to be equal to, we take the square of each of the components of our cross product vector, so -2, -4, and 1. We say -2 squared, we say -4 squared, and then we say 1 squared. We add those together, and then we take the square root of that sum. And that value is going to be the square root of 4 plus 16 plus 1. That'll give us the square root of 21. The square root of 21 is approximately 4.6. So if we were to measure it, we'd look at our cross product vector over here, and we should see that that cross product vector is measuring about 4.6 units. That'll be the length of that cross product vector.